There are exactly 3 objects we know came from another star system. The first one looked wrong, the second one looked normal, the third one, well, that's where things get interesting. On October 14th, 2025, Parker Solar Probe had a front row seat to the closest encounter with an interstellar visitor in human history. 4 million kilometers, close enough to see details, close enough to see structure, close enough to see if 3i Atlas was what everyone said it was, just another comet passing through. But when scientists went looking for those 4 hours of footage, they found a gap. Convenient gap. And according to someone on the inside, what Parker saw before that gap appeared wasn't ice and rock. Stay with us, because what we expose tonight changes everything we thought about what's crossing our solar system. If you're as captivated by this mystery as I am, hit like and subscribe so you don't miss anything as this story develops in real time. Let me know in the comments where you're watching from, your local time, and your honest take. Do you think we're being told everything about what Parker really saw out there? Part 1. Hook and latest break. Picture a clock, October 14th, 2025, 800 hours, coordinated universal time. The numbers glow on your screen. Now watch them tick forward. 8:01, 8:15, 900 hours, 10:30, 1100. Noon. The clock keeps moving, but something doesn't. During those 4 hours, the Parker Solar Probe swept past an object that came from beyond our solar system. The spacecraft's camera should have captured everything. Instead, when you pull up the archive today, you find a gap where those 4 hours should be. The official explanation is simple: corrupted data, packet loss, unrecoverable. But according to a leaked report from inside the mission team, that's not quite true. The raw feed was received, the data made it back to Earth, someone just decided you shouldn't see it. We're talking about 3i Atlas, the third confirmed interstellar visitor to cross our solar system. Astronomers discovered it in July 2025, and immediately the numbers looked wrong. This thing wasn't orbiting the Sun. It was passing through, following a hyperbolic trajectory that could only mean one thing. It came from somewhere else. Another star system, another neighborhood of the galaxy. Just passing through ours like a tourist on a highway, here for a brief visit before disappearing forever into the cosmic dark. Scientists scrambled to observe it with every telescope they could aim at the sky. They measured its composition, tracked its motion, analysed the light bouncing off its surface. What they found was strange enough to fill research papers: high carbon dioxide content, unusual polarization, behaviour that didn't quite match what comets normally do. But here's what makes October 14th so important. On that day, Parker Solar Probe was on its outbound leg, swinging away from one of its regular dives past the Sun. Pure coincidence put 3i Atlas within roughly 4 million kilometers of the spacecraft. That's nothing in space terms. That's closer than any other instrument has ever gotten to an interstellar object. WISPR, Parker's imaging system, was pointed in exactly the right direction. The geometry was perfect. If you wanted to get a good look at an alien visitor to our solar system, this was your shot. This was the moment. And according to mission protocols, WISPR should have been recording everything. Now let's talk about what allegedly happened next. Social media exploded first because social media always explodes first. Someone on a forum posted a screenshot of the data archive interface. They circled a gap in the file listings. Frame numbers jumped from PSP_00492 straight to PSP_00540. Where did the frames in between go? The post went viral. Within hours, hashtags were trending. Parker saw something. NASA hides alien probe. The usual mix of genuine curiosity and wild speculation. Then came the leak. An anonymous report, allegedly from someone with access to the mission's internal systems. The report claimed that the raw feed from those 4 hours did make it to the ground station. The frames were received, processed, and initially stored, but then someone added a packet loss flag to the data manually. The frames were re-indexed. They disappeared from public view. And according to this whistleblower, there's a reason someone wanted those frames hidden. The leaked report describes what the frames allegedly showed. A series of distinct equidistant thermal vents along a longitudinal axis. A hard shadow cast against the solar corona. A black monolith silhouette. Venting plasma. If this is true, it would mean Parker didn't photograph a comet or an asteroid. It photographed something that looked engineered. Something dumping heat in a controlled pattern. something with structure and geometry that nature doesn't produce on its own. Something, in other words, that might be artificial. We need to be absolutely clear about something before we go any further. Mainstream mission pages have not confirmed any of this. NASA has not released a statement about censorship or scrubbed data. The Johns Hopkins Applied Physics Laboratory, which operates Parker Solar Probe, has not acknowledged any unusual activity during the flyby. The leak is unverified. The screenshots could be misinterpreted or fabricated. The entire story might be a rumour that spiralled out of control. But we're going to treat it as a working hypothesis, because even if it's false, the questions it raises are worth asking. How transparent are space missions? What happens when extraordinary claims emerge from inside the scientific community? And what would it actually mean if an interstellar object turned out to be something more than rock and ice? This matters because 3I Atlas represents a unique opportunity. Interstellar visitors are rare. Before this one, we'd only confirmed 2 others, 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Both of them sparked intense scientific interest and yes, plenty of speculation about whether they might be artificial. Both times the answer turned out to be probably not. But we never got close enough to know for sure. They were too far away, moving too fast, and we didn't have spacecraft in the right position to intercept them. 3I Atlas is different. Parker was there. Parker had the view. If the data exists, it would be the first close-up visual record of an interstellar object ever captured. It would show us what these things actually look like when you're practically on top of them. It would answer questions we've been asking since Oumuamua first appeared and left us wondering. So here's what we're going to do over the next 2 hours. We're going to walk through this story piece by piece. We'll examine the timeline of the alleged data gap and figure out what it would take to actually scrub 4 hours from a mission archive. We'll look at the leaked descriptions of what Parker supposedly saw and evaluate whether they make any physical sense. We'll consider natural explanations that could produce vent-like features or shadow effects without requiring alien technology. We'll think about how institutions handle sensitive data and whether a cover-up scenario is even plausible. We'll zoom out and connect this to bigger questions about transparency in science, the credibility of extraordinary claims, and how we should respond when the evidence is incomplete, but the implications are enormous. And we'll do all of this without jumping to conclusions, because the worst thing we could do right now is pretend we know more than we actually do. One more thing before we dive in. If 3I Atlas really was artificial, if it really was some kind of probe or derelict craft from another civilization, what would that mean? It would mean we're not alone. It would mean someone else out there built machines capable of crossing interstellar space. It would mean they either visited our solar system deliberately, or their technology drifted through by accident. Either way, it would change everything. But we don't know that yet. We don't know anything yet. All we have are missing files, a leaked report, and a lot of questions. So let's start finding some answers. Part 2. Timeline and forensics of the archive claim. We need to reconstruct what happened, or what allegedly happened, minute by minute, October 14th, 2025. Let's start earlier in the day, before the window in question. Parker Solar Probe is in normal operations. It's travelling outbound from one of its close solar passes, which it does regularly as part of its mission to study the Sun's atmosphere and solar wind. WISPR, the wide-field imager for Solar Probe, is doing what it always does, taking pictures of the solar corona, tracking coronal mass ejections, monitoring solar activity. The data flows like it's supposed to. Frames are captured, stored in onboard solid-state memory, then beamed back to Earth when the spacecraft's high-gain antenna points toward home. Everything nominal. Then comes the critical window, 800 hours universal time. 3I Atlas is within roughly 4 million kilometers. That's close enough that WISPR should be able to resolve it as more than just a point of light. The object would still be small in the frame, but visible, detailed enough to show shape, activity, structure. The probe's instruments are recording. The data buffer is filling up. For the next 4 hours, Parker has an uninterrupted view of an interstellar visitor, while both objects move through space on their respective trajectories. This is the golden interval. This is when everything important should have happened. Afternoon universal time, according to publicly available information, operations resume as normal. Data downlink continues. The archive receives new frames. File numbers keep incrementing. Nothing seems unusual unless you look closely at the sequence. And this is where the forensic work begins, because if the leak is accurate, someone should be able to prove it just by examining the archive metadata. Let's talk about how Whisper data is supposed to work. The camera captures images and stores them on board in a buffer. When communication windows open and the spacecraft can point its high-gain antenna toward Earth, it transmits the data. Ground stations receive the transmission, forward it to the Mission Operations Center, and the data gets ingested into the archive. Each frame gets a file number, a timestamp, quality flags, and various metadata entries that describe exposure time, pointing direction, instrument settings. Under normal circumstances, these file numbers should be sequential. Frame PSP 00492 should be followed by PSP 00493, then 494, and so on. If you see a jump, something happened. Maybe the camera was turned off. Maybe the buffer filled up and older data was overwritten. Maybe a transmission failed and some frames never made it to the ground. Or maybe someone manually removed frames from the sequence and re-indexed what remained. The whistleblower claim specifically alleges that frames existed, were transmitted, were received, and were then flagged as corrupted after the fact. This would require manual intervention. Automated systems don't usually go back and relabel data that was already successfully ingested. If a packet is lost during transmission, the system flags it immediately during the downlink process. But if the data made it through, got stored, got processed, and then later someone decides it needs to be removed, that requires a human being with access to make a deliberate choice, and that choice should leave traces, log entries, metadata changes, timestamps showing when flags were added. This is the smoking gun that investigators should look for. Here's what you can do right now if you want to verify any of this yourself. Go to the official Parker Solar Probe Whisper archive. It's public. Anyone can access it. Find the data products from October 14th, 2025. Look at the file listings around 800 to 1200 hours universal time. Check the frame numbers. Are they sequential? Is there a gap? Look at the metadata for frames immediately before and after the alleged missing window. Do the timestamps make sense? Is there any indication of manual editing? Check the quality flags. If frames are marked as corrupted or missing, when were those flags added? Some file systems preserve modification timestamps. If a file was flagged weeks or months after the original ingestion date, that's suspicious. You should also look at earlier and later encounters for comparison. Pull up Whisper data from other solar passes. How do those sequences look? Are there gaps? How often does genuine data loss occur? If Parker has been operating for years with a near-perfect data retrieval rate, and then suddenly you get a 4-hour gap during the one moment when it's flying past an interstellar object, the coincidence is striking. Not impossible, but striking. On the other hand, if data gaps are common, if Whisper frequently loses frames due to thermal stress or antenna pointing constraints or buffer limitations, then maybe this gap is just another routine operational hiccup. Let's consider the technical details of what could go wrong legitimately. Parker operates in an extreme environment. It flies closer to the sun than any previous spacecraft. Temperatures on the heat shield reach thousands of degrees. Electronics have to be carefully protected. When the spacecraft is close to the sun, it can't always point its high-gain antenna toward Earth, because doing so would expose sensitive components to direct solar radiation. During those times, it stores data on board and waits for a safer geometry before transmitting. This creates natural gaps in the data flow, but those gaps are predictable and documented. Mission planners know when communication windows are available. They know when data will be stored versus when it will be transmitted. If the October 14th gap falls during a planned communication blackout, that would be one thing. But if the geometry was favourable and the antenna should have been pointing toward Earth, and data was nominally being transmitted, and then suddenly there's nothing, that raises different questions. There's also the possibility that data is still on board the spacecraft but hasn't been downlinked yet. Space missions sometimes prioritize certain data products over others. High-priority science observations get transmitted first. Lower-priority data might sit in the buffer for days or weeks until bandwidth is available. But Whisper data is central to Parker's mission. Imaging the corona is one of the probe's primary objectives. It's hard to imagine a scenario where 4 hours of imaging during a high-profile event would be deprioritized to the point of never being sent. And if the data is still on board, mission operators could command the spacecraft to retransmit it. This is standard practice when data is incomplete or lost. The fact that this allegedly hasn't happened, or if it has, the results haven't been made public, is part of what fuels the speculation, so we're left with a few possibilities. 1. The data was never captured because the camera was off or malfunctioning. 2. The data was captured but never successfully transmitted due to a communication failure. 3. The data was transmitted but corrupted during the transmission process. 4. The data was received intact but later removed or hidden for reasons unknown. The leak claims option 4, proving or disproving that requires access to internal logs, transmission records and metadata that the public typically doesn't see. This is why transparency matters. Without full access to the mission's operational data, we're left guessing. And when people are left guessing about something this important, speculation fills the void. Part 3. The geometric vents. Leak claim anatomy. Now let's talk about what the leaked report allegedly describes. We're going to take the claims seriously for the sake of analysis, but remember, these are unverified allegations from an anonymous source. No peer-reviewed paper supports this. No official mission statement confirms it. We're in speculative territory, but the speculation itself is worth examining because it reveals what people think is possible and what evidence would be required to support such a claim. The central claim is this. The Whisper frames from October 14th show a series of distinct equidistant thermal vents along a longitudinal axis. That phrasing is very specific. Distinct means they're clearly visible and separable from one another, not blurred or diffuse. Equidistant means they're spaced at regular intervals, like someone planned them that way. Longitudinal axis means they run along the length of the object, not scattered randomly. Thermal vents implies they're emitting heat or plasma, not just reflecting sunlight. If you saw something like that, you'd immediately think structure. You'd think engineering. You'd think someone built this thing with a specific purpose. The report also mentions a hard shadow cast against the solar corona. This is important because comets and asteroids don't usually cast hard shadows. They're surrounded by diffuse clouds of gas and dust called comas. When you look at a comet, you see a fuzzy blob with a tail, not a sharp silhouette. But if an object is solid and opaque, if it has defined edges and a relatively smooth surface, it could block light cleanly and create a shadow with distinct boundaries. Seeing a hard shadow would suggest a body with structural integrity, something that holds its shape instead of shedding material in all directions. Then there's the phrase black monolith silhouette. Monolith means a single, large block. Black means it's not reflecting much light. Silhouette means you're seeing it in outline, backlit by something brighter. Put it together, and you get an image of a dark, solid object seen against the bright background of the sun's outer atmosphere. This is evocative language, almost cinematic, and that's part of why the leak has gotten so much attention. It sounds like something from a science fiction movie. But that doesn't mean it's false. The universe is strange. Reality sometimes looks like fiction. Finally, venting plasma. Plasma is ionized gas, the fourth state of matter. You find it in the solar wind, in lightning bolts, in fusion reactors. If an object near the sun is venting plasma, it's actively dumping energy. It's not just passively reflecting light or sublimating ice. It's doing something dynamic. And if that venting follows a pattern, if it happens at regular intervals from specific locations on the surface, that implies control. That implies a system designed to manage heat or expel waste or generate thrust. That implies technology. So let's break this down into physical terms. What would thermal vents actually do for an object near the sun? The sun is hot. Really hot. Even at 4 million kilometers, the radiation flux is intense. Any object that glows needs to either absorb the heat and store it, reflect it, or get rid of it somehow. Natural objects like comets handle this by sublimating. Ice on the surface turns directly into gas, carrying heat away. But sublimation is messy. It produces a diffuse cloud. It's not focused or controlled. If you wanted to dump heat efficiently, you'd use a radiator system. You'd channel heat to specific vents or panels, eject it in concentrated streams, and keep the rest of your structure cool. That's what spacecraft do. That's what any machine operating in extreme temperatures would need. Now imagine you're looking at Whisper images, and you see exactly that pattern. Multiple bright jets emanating from specific points along the object's length. Each jet is equally bright, equally spaced, equally sized. They pulse on and off or maintain a steady flow. You measure the spacing and find it's regular to within a few percent. You check the spectrum and see it's ionized hydrogen and helium, not the typical mix of water vapor and organics you'd expect from a comet. You look for the diffuse coma and don't find one. Instead, you see a hard-edged silhouette, dark except for those bright vent points. What conclusion would you draw? Here's the problem. None of this is confirmed. We don't have the images. We don't have spectral data from that moment. We don't have independent corroboration from other instruments. All we have is a description in a leak, and descriptions can be wrong. They can be misinterpretations of ambiguous data. They can be exaggerations. They can be fabrications. So we need to ask, what could produce vent-like features without requiring alien technology? First possibility, instrumental artifacts. Cameras are not perfect. They have hot pixels, cold pixels, cosmic ray hits, glare, diffraction spikes. When you're imaging a very bright object like the solar corona and trying to pick out a faint target, you have to push the processing hard. You adjust contrast, subtract backgrounds, apply filters. Sometimes this creates ghost images. Sometimes scattered light inside the camera produces symmetrical patterns that look real but aren't. Sometimes compression errors or transmission glitches create streaks or repeating structures in the data. An experienced imaging scientist knows how to spot these artifacts and filter them out. But if someone less experienced looked at the raw frames, or if the processing pipeline had bugs, they might mistake artifacts for real features. Second possibility, natural but unusual outgassing. Comets can produce jets. These jets happen when sunlight heats up a localized patch on the surface, causing rapid sublimation. If the comet is rotating and has discrete active regions, the jets can appear periodic. They turn on when that region faces the sun and turn off when it rotates into shadow. From a distance, especially if you're not resolving the rotation clearly, this could look like synchronized venting. The jets might even line up along a rotational axis, giving the appearance of a longitudinal pattern. This is well-documented behavior in some comets. It's not common, but it happens. Third possibility, fragmentation. Maybe 3i Atlas isn't a single object, but a cluster of smaller pieces travelling together. Comets can break apart under tidal stress or thermal shock. If multiple fragments are venting gas independently, and they're strung out along the orbit, they could create multiple plumes that appear organised when viewed from certain angles. This would also explain why the object might have an unusual shape or structure. It's not one thing, it's many things pretending to be one. Fourth possibility, plasma interactions with the solar wind. The region near the Sun is full of charged particles, magnetic fields, and turbulent flows. When a comet passes through this environment, its coma can interact with the solar wind in complex ways. Magnetic field lines can channel plasma into streams or jets. Charged dust grains can clump together or align. Under the right conditions, you might see organized structures that are driven by electromagnetic forces, not by anything happening on the comet itself. This would be exotic but not unprecedented. Scientists have observed similar effects in laboratory plasmas and around other solar system bodies. Each of these explanations is plausible. Each one requires specific conditions, but none of them violate known physics. The problem is that without the actual data, we can't test them. We can't check whether the spectral signatures match natural outgassing or ionized plasma from a radiator. We can't verify whether the pattern is consistent across multiple frames, or if it appears only in a few processed images. We can't rule out artifacts without inspecting the raw sensor data. This is why the missing frames are such a problem. Without them, we're stuck in a realm of competing hypotheses with no way to decide between them. But let's be honest, if the leak is accurate, if those frames really show what's described, the most straightforward interpretation is that Parker photographed something artificial. You can propose natural explanations and some of them might work, but they all require adding complexity and special pleading. Sometimes the simplest answer is the right one. And if the simplest answer is that someone built a machine capable of surviving a close solar pass, and we just happened to catch it on camera, then we need to take that possibility seriously, not as proof, not as certainty, but as a hypothesis worth investigating. Part 4. Statistical and Operational Oddities. Let's talk about coincidence. Parker's solar probe has been operating since 2018. That's 7 years of continuous observations by the time of the 3i Atlas flyby. During those 7 years, the probe has completed dozens of close solar passes, captured thousands of images, and transmitted enormous amounts of data back to Earth. The mission has been extraordinarily successful. Data loss happens, of course. No space mission is perfect. There are communication dropouts, instrument glitches, buffer overruns, and unexpected thermal events. But serious, unrecoverable data gaps are rare. The systems are designed with redundancy and error correction precisely to avoid losing important observations. Now, we need to be careful here because the specific claim that the mission has a 99.4% data retrieval success rate appears to come from the same leaked source, not from official mission documentation. We haven't found that number in published papers or press releases, so treat it as part of the leak narrative, not as verified fact. But let's run with it for the sake of argument. If data loss is genuinely rare, if most of the time everything works as intended, then what are the odds that the one major gap happens to coincide exactly with the closest approach to an interstellar object? You can do rough probability calculations here. Suppose Parker operates for 10,000 hours per year. That's about 417 days. Over 7 years, that's roughly 70,000 hours of operations. If data gaps occur, say once every few thousand hours, and each gap lasts a few hours, then the total time lost might be a few dozen hours spread across the entire mission. Now, the critical window for 3i Atlas is 4 hours. The probability that a random 4-hour gap falls exactly during that 4-hour window is roughly the total gap time divided by the total mission time. Let's say total gap time is 40 hours out of 70,000. That gives a probability of about 0.057%, or roughly 1 in 1700. Not impossible, but unlikely. Of course, these numbers are hypothetical because we don't have access to the mission's full operational history. But the point stands. If data loss is rare, then losing data during a once-in-a-mission event is suspicious. It doesn't prove anything. Unlikely things happen all the time, but it raises questions. On the other hand, there are legitimate operational reasons why data might not be available from that specific window. Let's consider some of them. First, antenna pointing. Parker's high-gain antenna has to be carefully aimed to maintain communication with Earth. During certain parts of the orbit, especially near perihelion, the spacecraft has to protect itself from solar heat. It orients the heat shield toward the sun, which can limit the antenna's field of view. If the geometry during the 3i Atlas flyby was such that the antenna couldn't point toward Earth, data might have been stored on board but not yet transmitted. This is normal. The question is, has it been transmitted since? If not, why not? Second, thermal stress. Whisper operates in a brutal environment. The instrument is designed to handle heat, but there are limits. If temperatures exceeded safe thresholds during the flyby, operators might have powered down the camera temporarily to avoid damage. Again, this would be normal and prudent. But typically, such decisions are documented. Mission logs should show when instruments were turned off and why. If those logs exist and show a thermal shutdown during the critical window, that would support a benign explanation. If the logs don't show that, or if the data suggests the instrument was operating normally, that supports the leak's claims. Third, data prioritization. Space missions have limited bandwidth. Not everything can be sent at once. Sometimes teams have to choose which observations to downlink first. High-priority targets get sent immediately, lower-priority data waits. But here's the thing. An interstellar object flyby is exactly the kind of high-priority event that would justify bumping other data. It's scientifically valuable, publicly interesting, and time-sensitive. If mission planners knew 3i Atlas would be in view, they almost certainly would have prioritized capturing and transmitting that data. The fact that it's allegedly missing suggests either they didn't prioritize it, which seems odd, or they did prioritize it and something else happened. Now let's contrast the benign scenario with the conspiracy scenario. The benign scenario says data was lost due to normal operational issues. Maybe the camera was off, maybe the transmission failed, maybe the data is still on board and will be downlinked eventually. These things happen. No malice, no cover-up, just bad luck or routine technical problems. The conspiracy scenario says data was received intact, processed, reviewed, and then deliberately removed from public access because it showed something extraordinary that someone decided the public shouldn't see. This would require deliberate action by individuals with authority. It would leave a trail of evidence in logs and metadata, and it would carry enormous risk because eventually someone would notice and ask questions. If you wanted to investigate this properly, here's what you'd request. First, raw level 0 frames from the Whisper camera for October 14th, 800 to 1200 Universal Time. These are the unprocessed sensor outputs. If they exist, they should be in the archive. If they don't exist, there should be a record of why they don't exist. Second, engineering telemetry logs showing spacecraft state during that period. Antenna pointing, instrument power, thermal readings, buffer status, data, transmission rates. These logs are routinely kept. They'd show whether the camera was on, whether data was being recorded, and whether it was transmitted. Third, ground station logs showing what data was received and when. These logs track every bit that comes down from the spacecraft. If the frames were received, there will be a record. If they weren't, there will be a record of that too. Fourth, any internal communications or memos related to data quality or missing frames. If there was a legitimate data loss, there would likely be discussions among team members about what happened and whether anything could be recovered. If there was a deliberate suppression, there might be emails or messages coordinating that action. Either way, documentation should exist. Fifth, checksums and metadata for all files in the relevant time window. These technical details can reveal whether files were edited after the fact, whether flags were added manually, whether the archive was reorganized. Forensic examination of file systems can uncover these changes. All of this information should be accessible under normal data transparency protocols. Scientific missions, especially those funded by public agencies, are generally expected to make their data available. There may be embargo periods or restrictions on certain types of data, but eventually everything is supposed to be released. If specific requests are denied, that in itself is informative. It suggests someone has something to hide, or at minimum that normal transparency procedures aren't being followed. The uncomfortable truth is that proving a cover-up is hard. It requires access to internal systems and documents that outsiders don't usually get. But proving a benign explanation should be easy. If the data loss was normal and innocent, mission operators should have no problem explaining what happened, showing the relevant logs, and demonstrating that standard procedures were followed. The fact that, according to the leak, this hasn't happened is part of what keeps the story alive. Part 5. Immediate reactions and ecosystem. The leak hit social media like a bomb. Within hours of the first post's hashtags started trending. Parker saw the spaceship, NASA censoring truth, 3i Atlas revealed. YouTube thumbnails exploded with dramatic imagery. CGI renderings of dark alien probes, arrows pointing at blurry telescope images, all caps text promising shocking revelations. Reddit threads multiplied. Forum discussions went on for pages. People shared the alleged screenshots, debated the file number gaps, speculated wildly about what the hidden frames might show. Some were excited, some were skeptical, some were terrified. The story tapped into a primal human fascination. Are we alone? And if not, have we just found proof? This is how information spreads in the modern age. A claim emerges. It's compelling, maybe a little sensational, maybe backed by just enough detail to seem credible. People share it. Others amplify it. Within a day, millions have seen some version of the story, whether accurate or distorted. The original context gets lost. Facts get mixed with speculation. By the time mainstream outlets pick it up, the narrative has already solidified in the public mind, and once that happens, correcting misunderstandings becomes almost impossible. The scientific community responded differently. Astronomers who study comets and interstellar objects issued cautious statements. Yes, 3i Atlas is real. Yes, it's an interstellar visitor. Yes, it has some unusual properties. But no, there's no verified evidence of artificial structure. The object's orbit is hyperbolic, consistent with an interstellar origin. Ground-based telescopes have observed it for months. Spectroscopic measurements show carbon dioxide and other volatiles consistent with a comet. Polarimetric studies suggest dust grains in the coma. None of this requires invoking alien technology. It's all consistent with a natural object, albeit an unusual one. Several research papers were published or pre-printed describing 3i Atlas. One team reported high carbon dioxide abundance, higher than typical solar system comets but not impossible. Another analysed light curves and found variability suggesting rotation or irregular activity. A third looked at the polarization of reflected light and found values consistent with dusty cometary material. All of these studies were careful, methodical, and conservative. They presented data, discussed uncertainties, and avoided jumping to conclusions. This is how science is supposed to work. But here's the problem. Peer-reviewed papers don't go viral. Measured, cautious analysis doesn't generate clicks. The public sees a headline that says, "Scientists find unusual comet," and it barely registers. Meanwhile, the headline that says NASA hides alien probe footage gets shared 10,000 times. This creates a bifurcation in the information ecosystem. On one side, you have the scientific process, slow, deliberate, evidence-based. On the other side, you have the social media discourse, fast, emotional, speculation-driven. The two communities talk past each other. Scientists get frustrated that people ignore the evidence. The public gets suspicious that scientists are covering something up, or too close-minded to consider radical possibilities. This dynamic isn't new. It happens with every major astronomical discovery that captures public imagination. When Oumuamua was discovered in 2017, similar speculation erupted. Was it an alien probe? Was it a light sail? Harvard astronomer Avi Loeb argued publicly that we should consider the possibility seriously. Other scientists pushed back, saying natural explanations were sufficient, and invoking aliens was premature. The debate became polarized. Facts got tangled with opinions, and in the end, Oumuamua left the solar system without us ever resolving the question, definitively. The same thing happened with 2I/Borisov in 2019, though to a lesser extent because Borisov looked more clearly like a comet. And now it's happening again with 3I Atlas, except this time there's an added layer, the claim that data is being hidden. This transforms the narrative from interesting astronomical object to possible government cover-up. It activates people's distrust of institutions. It feeds into existing conspiracy theories about alien contact and suppression of evidence. It makes the story bigger than just the object itself. Media coverage reflects this split. Mainstream science outlets report on the comet's discovery, its unusual composition, and the scientific campaign to study it. They interview astronomers, cite research papers, and present the story as an exciting but fundamentally conventional piece of astronomy. Meanwhile, alternative media, independent YouTubers, and conspiracy-focused platforms run with the leaked claims. They highlight the missing data, question NASA's transparency, and argue that the scientific establishment is either complicit in a cover-up or too timid to acknowledge the obvious truth. The result is an information ecosystem where two incompatible versions of reality coexist. In one version, 3I Atlas is a weird but natural comet. In the other version, it's an alien spacecraft and evidence is being suppressed. People self-select into whichever version aligns with their priors. If you trust institutions and value peer review, you dismiss the leaker's unsubstantiated rumour. If you're skeptical of authority and believe governments hide things, you see the leak as confirming your suspicions. Neither side can convince the other because they're operating from different epistemological frameworks. This is dangerous for several reasons. First, it erodes trust in science. When people believe that scientists are hiding evidence or refusing to consider radical ideas, they stop listening to scientists about anything. Climate change, vaccines, evolution, all of it becomes suspect. Second, it makes rational discussion almost impossible. You can't have a productive conversation when one side thinks the other is either naive or complicit. Third, it distracts from real questions that deserve attention. Whether or not 3I Atlas is artificial, it's definitely interesting. It's definitely worth studying. The public fascination with this object could be channeled into genuine scientific engagement, into teaching people how astronomy works and why data transparency matters. Instead, it's being channeled into tribal conflict. So where does that leave us? We have a scientific consensus that 3I Atlas is most likely a natural object. We have a leak claiming that data exists showing otherwise. We have a public that's split between belief and skepticism. And we have institutions that, so far, haven't provided the level of transparency that would settle the question one way or another. The next act of this story will depend on what evidence emerges, if any, and whether anyone with access to the missing data decides to release it. Until then, we're stuck in uncertainty, and uncertainty is a breeding ground for speculation. Part 6. Imaging Forensics. Can Whisper be fooled? Let's talk about how cameras lie. Not intentionally, but cameras are not perfect eyes. They're instruments with limitations, quirks, and failure modes that can create images of things that aren't really there. If we want to evaluate the leaked claims about what Whisper supposedly saw, we need to understand how the imaging system works and what could go wrong. Whisper is a telescopic imager designed to photograph the Sun's outer atmosphere. It uses charge-coupled device sensors, similar to what you'd find in a high-end digital camera. but hardened to survive the radiation environment near the Sun. The camera captures raw frames that scientists call level 0 data. These are the direct readouts from the sensor, just numbers representing how much light hit each pixel. Then comes processing. Level 1 data means the raw frames have been calibrated, corrected for detector response, dark current subtracted, flat field corrections applied. Level 2 means further processing has happened, background subtraction, noise filtering, sometimes image stacking or deconvolution. Each processing step makes the images more useful for science, but also introduces opportunities for artifacts. Start with cosmic rays. These are high-energy particles that zip through space and occasionally smash into camera sensors. When a cosmic ray hits a pixel, it deposits energy and creates a bright spot that looks like a star or a hot pixel. A single cosmic ray hit is easy to spot and ignore, but if you're imaging for hours and cosmic rays keep hitting the sensor, you can accumulate dozens or hundreds of false bright spots. If those spots happen to line up by chance, or if your processing algorithm tries to connect them, you can create illusory structure. Image processing software is supposed to flag and remove cosmic ray hits, but the algorithms aren't perfect. Sometimes they miss hits, sometimes they flag real features as hits. You need human judgment to decide what's real and what's not. Next, consider detector imperfections. Every camera sensor has hot pixels that always read too bright, and cold pixels that always read too dim. Calibration files are supposed to correct for these, but if the calibration is off or if new hot pixels develop over time, they can create false features in the final image. Worse, if several hot pixels cluster together, they can look like a real object. You might see a line of bright pixels and think it's a jet of material, when actually it's just a strip of bad detector. Then there's glare and scattering. WISPR is trying to image faint objects against the extremely bright solar corona. That's like trying to photograph a mosquito hovering in front of a searchlight. The sensor gets flooded with light. Even with baffles and careful optical design, some of that light scatters inside the camera. It bounces off lens surfaces, reflects from mechanical parts, and creates ghost images. These ghosts can be symmetrical because optical systems often have symmetrical designs. You might see multiple copies of the same feature, evenly spaced, looking very much like distinct equidistant vents, but they're just reflections inside the camera. Compression is another issue. Data from spacecraft is often compressed before transmission to save bandwidth. Compression algorithms work by finding patterns and redundancies in the data. But aggressive compression can introduce artifacts, blocky regions, repeating patterns, edge enhancement that makes structures look sharper than they really are. If you compress an image of a fuzzy comet, then decompress it and process it, you might end up with features that look structured and geometric purely because of how the compression algorithm worked. Background subtraction is particularly tricky. When you're imaging the corona, you need to subtract the bright background to see faint objects. You take an image without the object, or an average of many images, and subtract that from your target image. But if your background model is wrong, you create false features. Maybe the corona wasn't uniform. Maybe there was a bright region that you subtracted too aggressively, leaving a dark spot that looks like a solid silhouette. Or maybe you didn't subtract enough, leaving a bright halo that looks like venting. The parameters you choose for background subtraction dramatically affect what the final image shows. Let's do a thought experiment. Imagine you have a WISPR frame showing the corona and a small faint object somewhere in the field of view. You want to bring out details on that object, so you crank up the contrast. You apply edge enhancement to sharpen features. You subtract the estimated corona brightness. You remove cosmic ray hits. You stack multiple frames to improve signal to noise. At each step, you make choices about parameters and thresholds. If you're not careful, or if you're pushing the processing too hard, you can create structure that wasn't there in the raw data. You can turn a fuzzy blob into a sharp-edged monolith. You can turn random noise spikes into a regular pattern of vents. And if you don't have the raw data to compare against, you'd never know you'd been fooled. This is where pareidolia comes in. Humans are incredibly good at seeing patterns, even in random noise. It's a survival trait. Better to mistake a shadow for a predator than to miss a real threat, but in science, this trait can mislead us. We look at a noisy image and our brains find faces, structures, shapes. The famous face on Mars is a perfect example. Viking orbiter images from the 1970s showed what looked like a giant face carved into the Martian surface. People saw eyes, a nose, a mouth. It looked artificial. But when later missions photographed the same region with better cameras and different lighting, the face disappeared. It was just a maser with shadows that happened to look face-like from one particular angle. Our brains filled in the rest. The same thing happens in astrophotography all the time. Amateur astronomers see structures in nebulae and give them names. The horsehead, the eagle, the pillars of creation. These names are useful and evocative, but they can also bias perception. Once you're told something looks like a horse's head, it's hard to see anything else. Similarly, if you're told an image shows geometric vents and a monolith, you'll look for exactly those features. Your brain will emphasize the parts that fit the description and ignore the parts that don't. So how do imaging specialists guard against this? First, they always check the raw data. If a feature appears in processed images but not in raw frames, it's probably an artifact. Second, they look at multiple frames. Real features should be consistent across time. Artifacts are often random or vary from frame to frame. Third, they cross-check with other instruments. If Whisper sees something unusual, do other cameras or detectors see it too? If not, that's a red flag. Fourth, they use conservative processing. Better to miss a faint real feature than to create a convincing fake one. And fifth, they publish their methods. Peer review means other scientists can try to reproduce your results using the same data and see if they get the same answer. None of this has happened with the 3i Atlas alleged imagery because, according to the leak, the data hasn't been released. We don't have raw frames to inspect. We don't have multiple independent analyses. We just have a description claiming that processed frames show certain features. Without the ability to verify, we have to consider the very real possibility that what was seen, if anything was seen, was an artifact of the imaging and processing pipeline, not a real object. Here's the uncomfortable question. Could a knowledgeable insider deliberately create a fake image that looks convincing? The answer is yes. If you have access to raw data and processing tools, you could manufacture features. You could add bright spots in specific patterns. You could edit frames to show structure that wasn't there. You could generate metadata that makes it look like the fake frames came from the real mission. This is why data provenance matters. You need an unbroken chain of custody from the sensor to the final image, with checksums and logs at every step, so you can verify that nothing was altered. If that chain is broken, or if someone with access tampered with the data, distinguishing real from fake becomes almost impossible. So when we hear claims about geometric vents and hard shadows, we have to ask, are these real features captured by Whisper, or are they artifacts of processing, instrumental glitches, human pareidolia, or even deliberate fabrication? Without access to the original data, we simply cannot say. And that's exactly why the missing frames are such a problem. They leave us in a position where we can't verify, can't falsify, can't do science. We're left with claims and no way to check them. That's not how this is supposed to work. Part 7. Physical hypotheses that could mimic vents. Scientists don't jump to alien explanations. That's not because they're closed-minded or unimaginative. It's because history has taught them that when you see something weird, there's usually a natural explanation you haven't thought of yet. So before we accept the hypothesis that Parker photographed an artificial object, we need to seriously consider what natural processes could produce vent-like features, regular geometry, and hard shadows. Let's walk through several plausible scenarios. Hypothesis. A. Rotationally modulated sublimation from discrete active regions. Comets are lumpy, irregular objects. They're not smooth spheres. They have craters, cliffs, fractures, and patches of different composition. When a comet approaches the Sun, some areas heat up faster than others. Ice trapped under a dark dust layer might suddenly break through and start venting gas. If these active regions are distributed around the comet's surface, and if the comet is rotating, you'll see jets that turn on and off as the active patches rotate into sunlight, and then back into shadow. From a distance, especially if you're not resolving the rotation clearly, this could create the appearance of periodic equidistant vents. The spacing would be determined by the rotation period and the locations of the active regions. It wouldn't be engineered, but it could look organized. This hypothesis makes predictions. You should see the vents pulsing with the rotation period. You should detect changes in gas production rate that correlate with rotation. Spectroscopy should show typical cometary volatiles. Water, carbon monoxide, carbon dioxide, maybe some organics. The jets should be diffuse, not focused. And if you observe the comet over several rotations, the pattern should repeat consistently. Ground-based telescopes could test all of this. If observations match these predictions, then rotationally modulated sublimation is a strong candidate. If they don't, if the pattern is too regular or the spectrum is wrong, then you need a different explanation. Hypothesis. B. A fragment train or debris cluster. Suppose 3I Atlas isn't a single solid body, but a collection of smaller pieces travelling together. Comets can shatter under tidal stress when they pass too close to a planet or the Sun. They can also break apart due to rapid rotation or internal pressure from sublimating ice. If 3I Atlas fragmented at some point before the Parker encounter, you might have multiple boulders or chunks spread out along the orbit. Each fragment could be venting independently. From WISPR's perspective, seeing multiple venting sources aligned in space might look like a single object with regularly spaced vents. The hard shadow claim could be explained if the fragments partially overlap from WISPR's viewing angle, creating a composite silhouette that looks more solid than it really is. This hypothesis also makes predictions. You should be able to resolve individual fragments with high-resolution imaging. Light curves should show complex irregular variability as different fragments rotate and vent at different rates. Non-gravitational acceleration should be erratic, not smooth, because each fragment is pushing in a slightly different direction. Spectroscopy might show variations between fragments if they have different compositions. Again, ground-based observations could test this. If telescopes see multiple distinct objects where we thought there was one, the mystery is solved. Hypothesis C. Plasma interactions with solar wind and magnetic fields. The space near the Sun is not empty. It's filled with charged particles streaming outward in the solar wind, tangled magnetic field lines, and complex electromagnetic structures. When a comet passes through this environment, its coma interacts with the solar wind. Ions in the coma get picked up by the field and accelerated away, forming a plasma tail. Under certain conditions, magnetic reconnection events or current sheets can create focused flows of plasma. These flows might appear as jets or beams. If the geometry is just right, you could see multiple plasma streams aligned in a way that looks structured. The streams wouldn't be coming from the comet itself, but from the surrounding space environment. This is exotic, but not impossible. Scientists have observed similar phenomena at other solar system bodies. For instance, magnetic field draping around Venus creates complex structures. Io's volcanic plumes interact with Jupiter's magnetosphere to produce auroral emissions and plasmatorus features. The Sun's corona itself is full of filaments, loops, and jets driven by magnetic processes. It's conceivable that 3I Atlas, with its coma and outgassing, could trigger some kind of electromagnetic instability that produces visible plasma features. If this is what WISPR saw, it would be fascinating science, but not evidence of technology. Testing this hypothesis requires magnetometer data. Parker has a magnetic field instrument. If there were unusual magnetic signatures during the 3I Atlas flyby, that would support the plasma interaction idea. You'd also expect to see variability. Magnetic structures are dynamic and change on short timescales. The features shouldn't be perfectly stable or symmetrical unless something is actively controlling them, which brings us back to the artificial hypothesis. Hypothesis D. Explosive outgassing from subsurface volatile reservoirs. Imagine 3I Atlas has pockets of highly volatile material, like carbon monoxide or nitrogen, trapped beneath a crust of less volatile ice. As the object heats up near the Sun, pressure builds in these reservoirs. Eventually, the crust ruptures and the volatiles explode outward in focused jets. If there are multiple reservoirs at regular intervals, perhaps due to some internal structure or layering, you could get multiple jets with roughly even spacing. The jets would be powerful and collimated, unlike the gentle diffuse sublimation from water ice. They might appear sharp and vent-like. This mechanism has been proposed for some of the geysers on Enceladus and the jets on comets like 9P/Tempel 1. It's more violent and dramatic than simple sublimation, but it's still a natural process. The predictions here are high-velocity gas, possibly detectable in spectroscopy as Doppler-shifted lines, dust and chunks of ice carried along with the gas, creating a collimated plume, possible changes in the jets over time as different reservoirs rupture and deplete. And again, spectroscopy should show normal cometary composition, not anything exotic. Each of these hypotheses keeps us within the realm of known physics. They require specific conditions, maybe even unusual or rare conditions, but nothing that violates our understanding of how nature works, and that's important. Invoking alien technology is a much bigger leap than invoking rare but natural phenomena. If we can explain the observations with natural processes, we should do that first. Only if natural explanations fail comprehensively should we start considering artificial origins. But here's the catch. We don't have enough data to test these hypotheses properly. The ground-based observations of 3I Atlas are limited. Telescopes have measured its orbit, brightness, colour, and some spectral features. But detailed imaging, high-resolution spectroscopy, time-resolved photometry, polarimetry, all of this is sparse. The Parker flyby could have provided the missing piece. Close-up images that reveal the object's structure and behaviour in detail. If those images exist and show natural comet-like features, great. If they show something that defies all natural explanations, that's when things get interesting. But without the images, we're just guessing. Part 8. The Alive Era Machine. Hypothesis. Rigorous interrogation. Alright, let's take the artificial hypothesis seriously. Not because we have proof, but because if we're going to rule it out, we need to understand what it would actually require and what evidence would support it. So let's ask, what would a machine designed to survive a close solar pass look like, and would it match what the leak describes? First, thermal management. Anything within a few million kilometers of the sun experiences intense heating. Surface temperatures can reach thousands of degrees. Materials melt, electronics fail, structures warp, a natural comet handles this by ablating. The surface vaporizes and carries heat away. But a machine can't afford to ablate continuously. It needs to maintain structural integrity, so it would use active thermal control, radiators to dump waste heat, insulation to protect sensitive components, possibly even a heat shield oriented toward the sun. The radiators would need to be efficient and they'd need to vent heat in a controlled way. That means focused exhaust streams, probably plasma or superheated gas, expelled from specific points on the hull. This is exactly what the leak describes: thermal vents along a longitudinal axis. Second, structural design. A spacecraft designed for interstellar travel would likely be elongated rather than spherical. A long, narrow shape minimizes cross-sectional area for radiation and impacts. It also makes sense for a propulsion system with thrust along one axis. You'd expect a rigid hull, possibly with modular sections. You'd expect symmetry because symmetry is efficient for engineering. You can repeat components, balance forces, simplify construction. So a hard shadow and geometric layout wouldn't be surprising. In fact, those features would be expected. Third, propulsion or attitude control. If the object is actively controlled, it might adjust its orientation or trajectory. This would show up as non-gravitational acceleration. The object's path deviates slightly from what pure gravity would predict. Comets also show non-gravitational acceleration due to outgassing, but the pattern is different. Comet jets are asymmetric and variable. They create torques that affect rotation. A propulsion system would produce thrust that's more consistent and directed. If 3I Atlas's trajectory shows anomalies that don't fit the comet outgassing model, that's a clue. Fourth, emissions. An active machine might generate electromagnetic signals, radio transmissions for communication, radar for navigation, waste heat in infrared, charged particle streams that interact with the solar wind. These signatures would be detectable, at least in principle, by Earth-based instruments, or by probes like Parker itself. If there were unusual magnetic field anomalies, radio bursts, or particle flux changes during the flyby, that would support the machine hypothesis. If there were none, that argues against active systems, though it doesn't rule out a derelict or dormant craft. Now let's consider the origin question. If 3I Atlas is artificial, where did it come from? Its hyperbolic orbit means it came from interstellar space. It didn't originate in our solar system, so either it was sent here deliberately, or it's drifting and happened to pass through. If it's deliberate, that implies an intelligence that knew about our solar system and wanted to investigate. That raises huge questions about intent, technology level, and whether there's ongoing observation. If it's drifting, it might be a derelict from some ancient civilization, travelling through space for millennia or longer, no longer functional, just coasting on its original trajectory. How would we distinguish between a functional probe and a derelict? A functional probe might adjust its course, emit signals, or respond to stimuli. It might even attempt communication if it detected our presence. A derelict would be passive. It would follow a ballistic trajectory. It might still vent heat if some onboard systems are running on decay heat or residual power, but it wouldn't show purposeful behavior. The leak describes venting, which could be consistent with either scenario: active radiators or passive thermal release from a dead machine that's still hot inside. Let's also think about the implications if this is real. Discovery of alien technology would be the most important event in human history. It would confirm that intelligent life exists elsewhere. It would prove that interstellar travel is possible. It would raise the question of whether we're alone in the galaxy or whether civilizations are common. It would spark a massive scientific effort to learn everything possible. What materials is the object made from? What propulsion system does it use? Is there any data storage or records we could access? What was its mission? Governments would get involved. Space agencies would scramble to plan follow-up missions. SETI programs would intensify. The public reaction would be enormous. But here's the problem. Extraordinary claims require extraordinary evidence. The leap from unusual comet to alien spacecraft is gigantic. It requires not just one piece of evidence, but multiple, independent, robust pieces. You need imaging that clearly shows artificial structure. You need spectroscopy showing non-natural materials or isotopic ratios. You need detections of artificial signals or unusual physical phenomena. You need consistency across multiple instruments and observation windows. And you need all of this to survive skeptical peer review by experts who will look for any possible alternative explanation. Right now, we don't have that. We have a leak. We have missing data. We have an unusual comet that's already been explained at least partially by natural processes. That's not enough. Not remotely. If the whisper frames exist and show what's claimed, that would be a significant step. But even then, you'd need to rule out instrumental artifacts, prove the images are authentic, and cross-check with other data. It's a high bar, and rightly so, because the consequences of getting it wrong are severe. If we falsely claim to have found alien technology, we undermine public trust in science. We create a credibility crisis. We embolden conspiracy theorists and make it harder to communicate real discoveries in the future. On the other hand, if we dismiss real evidence because we're too skeptical or too invested in conventional explanations, we miss the discovery of a lifetime. Balancing these risks is difficult. The approach scientists generally take is to assume natural explanations until they're exhaustively ruled out. It's not perfect, but it's the best method we have. So where does that leave the machine hypothesis? It's on the table. It's not crazy. It's not impossible, but it's low probability until we get better evidence. If the missing data surfaces and supports it, we'll have a very interesting conversation. If not, the hypothesis will remain speculative, a compelling what-if, but nothing more. Part 9. Leaks, whistleblowers, and institutional behavior. Let's talk about how big science missions actually work, because understanding the operational structure helps us evaluate whether the conspiracy scenario is plausible. Parker Solar Probe is managed by the Johns Hopkins Applied Physics Laboratory under contract to NASA. The mission involves hundreds of people: engineers, scientists, data specialists, mission planners, administrators. Data flows through multiple checkpoints. It's recorded on board, transmitted to ground stations, ingested into mission databases, processed by automated pipelines, reviewed by quality control teams, archived, and eventually released to the public. At every step there are logs, timestamps, checksums, version control. The system is designed to be robust and transparent precisely to prevent data loss or tampering. So who would have access to raw whisper frames before they're publicly released? The instrument team, certainly. These are the scientists and engineers responsible for the camera. They see the data first, they calibrate it, process it, and decide what's worth highlighting in publications or press releases. Mission operations personnel also have access because they need to monitor instrument health and performance. Data management staff have access because they ingest and archive the files. Quality assurance specialists review data products to ensure they meet standards. That's dozens of people, maybe more. Any of them could be the source of the leak, if the leak is real. Now let's think about what it would take to suppress data. First, someone with authority would need to make the decision. Instrument team leaders, mission principal investigators, or higher-level administrators. They'd need a reason. Maybe the data shows something so unexpected that they want time to verify before going public. Maybe there's concern about public reaction or misinterpretation. Maybe there are national security implications, though that's hard to imagine for comet imagery. Whatever the reason, they'd issue instructions. Flag these frames as corrupted, remove them from the public archive, don't talk about them externally. Executing that decision requires technical action. Engineers would need to modify the archive database. They'd add quality flags marking the frames as bad data. They might re-index surrounding files to hide the gap. They'd need to ensure that any automated systems checking for missing frames don't raise alarms. This leaves digital footprints, log entries showing who made changes and when, metadata alterations, version history. In a well-managed system, these footprints are auditable. An investigation could reconstruct exactly what happened. But here's the weakness: humans. The more people involved in a cover-up, the harder it is to maintain. Someone feels ethically conflicted. Someone thinks the public has a right to know. Someone is frustrated that exciting data is being buried. That person becomes a whistleblower. They copy files, take screenshots, write up an internal report and leak it to journalists or online forums. This is exactly the scenario described in the 3i Atlas story. An insider with access who decided to blow the whistle. Whistleblowing in science is complicated. Unlike corporate or government whistleblowing, where there are legal protections for exposing fraud or misconduct, scientific whistleblowing often operates in a grey area. If you're exposing data fabrication or ethical violations, you might have institutional support. But if you're leaking data that your organization decided to withhold for legitimate reasons, you could face professional consequences. You might get fired. You might be blacklisted in your field. You might face legal action if you violated non-disclosure agreements or data access policies. This creates a chilling effect. People with knowledge of wrongdoing or suppressed information might stay silent because the personal cost is too high. On the other hand, some people feel strongly enough about transparency and truth that they're willing to risk their careers. We've seen this in other contexts. Edward Snowden leaking NSA surveillance programs, Chelsea Manning releasing classified military documents, various scientists over the years exposing data manipulation or censorship. Whether you view these actions as heroic or reckless depends on your values, but they happen. Let's consider motives for suppression. Why would mission leadership hide data? One possibility: they genuinely believe the data is corrupted or unreliable, and they don't want to confuse the public with bad information. This is benign, though arguably too paternalistic. People can handle uncertainty and bad data if you explain the situation clearly. Another possibility: the data shows something so strange that they want to study it privately before announcing, to avoid embarrassment if they got it wrong. This is understandable but problematic, because science is supposed to be open. Discoveries should be shared, not hoarded. A third possibility: the data shows something extraordinary, and there's concern about public panic, national security, or loss of funding. This gets into darker territory, where institutional interests override scientific integrity. There's also the question of precedent. Have NASA or other space agencies suppressed data in the past? The answer is complicated. There have been cases where data was embargoed for specific reasons: national security classifications on reconnaissance satellite imagery, proprietary restrictions on commercial launches, delays in releasing data to give mission teams time to publish first. But outright censorship of scientific data to hide evidence of alien life or technology? There's no documented case of that. It's the stuff of conspiracy theories, not historical record. That doesn't mean it couldn't happen, but it does mean the burden of proof is high. If the 3i Atlas suppression is real, it would be unprecedented. It would represent a decision by institutional leadership to hide potentially the most important discovery in human history. That's a massive choice. It implies either extraordinary timidity or something more sinister, and it implies that everyone involved in the decision, everyone who knows about the hidden data, has stayed silent except for one whistleblower. That's possible, but it requires a level of coordination and secrecy that's hard to maintain in an organization with hundreds of people. So what should happen next? If the allegations are serious, there should be an investigation. An independent body, not affiliated with the mission, should review the data archives, examine the logs, interview personnel, and determine whether data was improperly flagged or removed. This would be similar to scientific misconduct investigations that happen when someone is accused of fabricating results. The process is rigorous and transparent. If misconduct is found, there are consequences. If the allegations are baseless, that's documented and the accused are cleared. The problem is that such investigations require institutional will. Someone with authority has to authorize it. If the people who would authorize the investigation are the same people who allegedly suppressed the data, you have a conflict of interest. This is where external pressure matters. Journalists asking questions, scientists demanding transparency, public interest forcing the issue. Transparency mechanisms like Freedom of Information Act requests, though those have limitations and can be slow. Congressional oversight if the issue becomes politically significant. The court of public opinion, which isn't perfect but sometimes forces action when formal mechanisms fail. We should also talk about what transparency should look like. At minimum, raw data should be publicly archived within a reasonable timeframe, with clear documentation of any gaps or issues. Processing methods should be described in enough detail that independent researchers can replicate results. Logs showing data quality decisions should be available for audit. And when extraordinary claims emerge, mission teams should respond publicly, either confirming or explaining why the claims are inaccurate. Silence in the face of serious allegations only fuels speculation. Right now, that's not happening, whether because the allegations are false and don't merit response, or because there's active suppression, or because institutional inertia prevents action. The result is the same. We're stuck in a state of uncertainty, and that uncertainty is corrosive. It feeds mistrust, enables conspiracy theories, and distracts from legitimate scientific work. If transparency is the solution, then institutions need to prioritize it, even when it's uncomfortable or inconvenient. Part 10. Simulation. If we had the 4 hours. Let's run a thought experiment. Imagine, for the next few minutes, that the leak is completely accurate. The whisper frames exist. They were received on October 14th, processed, reviewed, and then quietly archived away from public view. Now imagine someone with access decides to release them. The files appear online, anonymously posted, unencrypted, available for anyone to download. What would those frames show, and what would happen next? Frame 1. The image is mostly black. The solar corona glows off to one side, a brilliant arc of light overwhelming part of the field of view. In the center, there's a silhouette. Dark, angular. Not the fuzzy irregularity of a comet's coma, but something with edges. Something that blocks light cleanly. The shape is elongated, maybe cylindrical or rectangular, hard to tell at this resolution, but it's clearly solid, clearly distinct from the background. No diffuse halo of dust and gas. Just the object itself, stark against the luminous backdrop of the sun's outer atmosphere. Frame 2. The view has shifted slightly as Parker moves along its trajectory. Now you can see more detail. Along one side of the silhouette there are bright points, 6 of them, maybe 7. They're evenly spaced, running along what appears to be a longitudinal axis. Each point is glowing intensely, brighter than the surrounding darkness of the hull. These are the vents. They're emitting something, plasma or ionized gas, hot enough to shine against the corona's glare. The emissions aren't diffuse, they're collimated, focused, like exhaust from a rocket nozzle, and they're synchronized, all venting at the same rate, same intensity. Frame 3. A different angle. The object has rotated slightly, or Parker's position has changed enough to reveal another face. The structure becomes clearer. It's not irregular like a natural object. There are flat panels, geometric sections, possibly seams where components join together. The proportions suggest deliberate design, a central spine with modules attached, or a layered architecture with distinct functional regions. This isn't something that accreted from dust and ice. This isn't something shaped by random collisions and erosion. This is something built. Frame 4. The thermal signature is intensifying. The vents are glowing brighter now, maybe because the object is heating up as it swings closer to perihelion, or maybe because some internal system has activated. The plasma streams are visible as extended jets, reaching away from the hull. They shimmer and fluctuate but maintain their organized pattern. In the background, the solar corona churns and roils, massive loops and prominences dwarfing the tiny silhouette. The contrast is humbling, a fragile machine navigating the most hostile environment in the solar system, dumping heat to survive. Frame 5. One last glimpse before the geometry becomes unfavorable, and Whisper loses the view. The object is receding now, or the camera is panning away. But for a moment, everything is clear. The hull, the vents, the structure. If this were released, scientists would analyze every pixel. They'd measure the dimensions, estimate the mass, calculate the thermal output. They'd compare the spectrum of the vent emissions to any known natural or artificial source. They'd look for patterns in the timing or intensity that might encode information. They'd cross-reference with any other data from Parker's other instruments, magnetometer readings, plasma detectors, radio receivers, and then the phone calls start. Every major observatory on Earth scrambles to reacquire 3i Atlas. Ground-based telescopes, radio arrays, space-based infrared missions, everything that can be pointed at the object. The goal? Confirm independently what Whisper saw, get higher resolution images, measure the spectrum in detail, detect any non-gravitational forces or unusual emissions. The observation campaign would be unprecedented, coordinated internationally, data shared in real time. This would be bigger than any single mission or institution. Simultaneously, the media explodes. News outlets around the world run with the story. Alien probe photographed near Sun, evidence of extraterrestrial technology. Experts are interviewed. Some urge caution. We need more data. We need to rule out alternatives. Others are more willing to speculate. This could be the proof we've been waiting for. Public reaction ranges from excitement to fear to disbelief. Social media becomes a chaotic mess of takes, memes, theories, and arguments. Governments issue statements, mostly versions of "we're aware and investigating." Behind the scenes, space agencies convene emergency meetings. Can we send another mission to intercept 3i Atlas before it leaves the solar system? The object is moving fast on a hyperbolic trajectory. It won't be back. This is our only chance. Launch windows are calculated, delta-V requirements assessed. Existing spacecraft might be retasked if their trajectories allow. New missions might be proposed, fast-tracked through approval processes that normally take years. The goal? Get close enough to study the object in detail, maybe even rendezvous and conduct a physical inspection. CT programs ramp up efforts. If this object was sent here deliberately, maybe it's transmitting, maybe it's receiving. Radio telescopes scan for signals. Attempts are made to communicate just in case there's anyone or anything listening. Messages are composed, simple mathematical. Sequences, images depicting our solar system and Earth, expressions of peaceful intent. It's a long shot, but if there's even a tiny chance of response, it's worth trying. Within the scientific community, debates intensify. Some researchers argue that this is the most important discovery in history and demands radical openness. All data should be released immediately. All analysis should be collaborative. All results should be openly accessible. Others worry about premature conclusions. We need rigorous peer review. We need to eliminate all alternative hypotheses. We need to avoid another arsenic life debacle, where excitement outpaced evidence. The tension between speed and rigor becomes acute. But there are darker possibilities too. If the object is confirmed to be artificial, what does that mean for humanity's place in the universe? We are not alone. Someone else is out there, and they have technology capable of interstellar travel. That's inspiring, but also unsettling. What were their intentions? Is this object a probe sent to study us? A derelict from a long-dead civilization? A scout for something larger? Are there more of them? Has Earth been under observation this whole time without us knowing? The questions pile up faster than answers can be found. And what about the institutional response? If it turns out that data really was suppressed, there will be consequences. Investigations, resignations, reforms, demands for accountability, trust in space agencies, already fragile in some quarters, takes a hit. But there might also be understanding. Maybe the decision to withhold was made cautiously, out of a desire to be certain before making such an extraordinary announcement. Maybe the people involved were trying to do the right thing in an impossible situation. Public reaction might split. Some calling for heads to roll, others willing to forgive in light of the discovery's magnitude. All of this from 4 hours of missing footage. All of this from a few frames showing something that doesn't quite look like a comet. All of this, if the leak is true. But right now, it's just a thought experiment, a vision of what could be. Until those frames are released, if they exist at all, this remains in the realm of speculation. Still, it's worth imagining because it helps us understand the stakes. It helps us see why transparency matters and why these questions can't be dismissed out of hand. Part 11. Parallel. AGI, secrecy, and verification culture. Let's step back from comets and spacecraft for a moment and think about a parallel issue unfolding right now in a completely different field. Artificial general intelligence. In late 2025, we're seeing a historic race to develop AGI systems that could match or exceed human cognitive abilities across a broad range of tasks. Companies like OpenAI, Anthropic, DeepMind, and others are making rapid progress. Each new model release brings capabilities that would have seemed impossible just a few years ago. But with that progress comes a question that sounds very familiar. How much should be kept secret, and how much should be shared? The arguments for secrecy in AGI development are straightforward. Advanced AI systems could be dangerous if misused. They could be weaponized, used for mass surveillance, or cause economic disruption if deployed recklessly. The companies developing these systems argue that responsible development requires careful control, limited access, staged rollouts, and keeping certain technical details proprietary to prevent bad actors from replicating the most powerful capabilities. There's also competitive pressure. Billions of dollars are at stake and no company wants to give away its advantages. But there's a counter-argument that sounds like what we've been discussing with Parker Probe and 3i Atlas. Transparency enables verification, and verification enables trust. If AI companies make claims about their system's safety or limitations, how can we verify those claims without access to the underlying models and data? If something goes wrong, if a system behaves unexpectedly or causes harm, how can we investigate without transparency? And if we're making decisions about regulation, deployment, or research priorities, how can we do that informed by incomplete or filtered information? In December 2025, this debate intensified. Reports emerged of whistleblowers from major AI labs claiming that safety protocols were being bypassed, that concerning capabilities were being developed faster than safety measures, and that internal warnings were being ignored. The companies involved denied wrongdoing and pointed to their public commitments to responsible AI. But without transparency, without independent audits, without access to the actual systems and development processes, the public is left in the same position we find ourselves with the 3i Atlas data. We have claims, counterclaims, and no way to verify who's right. This is where we can draw direct lessons. Both cases involve cutting-edge technology with potentially transformative implications. Both involve institutions claiming to act responsibly while limiting external scrutiny. Both involve questions of public interest versus proprietary control. And both involve the risk that secrecy, even when well-intentioned, breeds mistrust and speculation. What would a transparency framework look like? Start with independent oversight. Third-party auditors with technical expertise should have access to systems, data, and processes. They can verify claims, identify risks, and provide accountability without necessarily making everything public. Think of this like the International Atomic Energy Agency for nuclear facilities. Inspectors ensure compliance without revealing weapons designs. Next, data escrow and mirrors. Critical data, whether it's whisper frames or AI training datasets, should be archived in multiple locations with different custodians. If the primary holder refuses to release data, secondary archives can step in. This redundancy prevents any single entity from suppressing information. Public logging and audit trails. Every significant action should be recorded. When data is flagged as corrupted, when access permissions are changed, when analysis decisions are made. These logs should be cryptographically signed and time-stamped, creating a tamper-evident record. Investigators can trace exactly what happened and when, making cover-ups much harder. Stage disclosure with safeguards. Not everything can be released immediately, especially if there are legitimate security concerns. But there should be a presumption of eventual disclosure. Embargo periods can be acceptable if they're time-limited, clearly justified, and subject to review. After a reasonable period, everything should be made public unless there's an ongoing, specific reason for continued restriction. Finally, cultural change toward openness as default. Scientific institutions and tech companies need to internalize the principle that transparency strengthens credibility, not weakens it. When you hide information, you invite suspicion. When you share, you build trust and enable collaboration. The strongest science happens in the open, with peer review and replication. The same should be true for any field with significant public impact. The AGI situation offers a warning for how the 3i Atlas story might unfold. If transparency isn't prioritized, if institutions continue operating behind closed doors, trust will continue eroding. People will assume the worst, conspiracy theories will flourish, and when a real breakthrough or crisis occurs, we won't have the verification mechanisms in place to handle it properly. On the other hand, if we can build better transparency norms now in both AI and space science, we'll be prepared when something truly extraordinary happens. Here's the call to action: demand openness. Not naively, not without considering legitimate security and safety concerns, but as a default principle that requires strong justification to override. Whether we're talking about missing spacecraft data or opaque AI development, the pattern is the same. Secrecy breeds problems. Transparency, though harder and messier, is how we build systems that work in institutions that deserve trust. Part 12. Parallel. New neutrino Qajar particle results and instrument trust. In late 2025, the neutrino physics community celebrated a milestone. New results from the Deep Underground Neutrino Experiment in South Dakota. The experiment detected rare neutrino oscillations with unprecedented precision, constraining parameters in the Standard Model and providing clues about matter-antimatter asymmetry in the early universe. The result was exciting, potentially transformative. But what's more interesting for our purposes is how the announcement was made and how the scientific community responded. Before publishing, the collaboration spent months checking their data. They looked for systematic errors, instrumental artifacts, calibration issues. They ran blind analyses where the people processing data didn't know what answer they were expected to get, preventing confirmation bias. They cross-checked against other neutrino detectors, including experiments in Japan and Antarctica. They shared preliminary results with other teams and invited criticism. Only after this exhaustive process did they publish their findings and hold a press conference. Even then, the reaction from the broader physics community was cautious enthusiasm. Other scientists praised the work but noted that replication would be needed before the results are fully accepted. Plans were made for independent analyses using different methods. Theorists started working on implications but hedged their conclusions. If the results hold up, then we might see certain predictions. This is how science is supposed to work. Extraordinary claims, even ones backed by strong data, are treated with skepticism until they're thoroughly vetted. Contrast this with the 3i Atlas situation. We have a claim of extraordinary observations based on a leaked report, not a published paper. There's no peer review, no independent replication, no cross-checks with other instruments, no blind analysis to prevent bias. The community hasn't had a chance to scrutinize the data because the data allegedly isn't available. And yet the claim is spreading, as if it's established fact in some circles. This highlights a fundamental asymmetry in how information flows. In legitimate science, there's a bottleneck: peer review. It's slow, sometimes frustrating, often imperfect, but it serves a purpose. It forces researchers to document their methods, justify their conclusions, and address criticism before going public. This bottleneck filters out a lot of bad work. Not all of it, certainly, but enough that when something makes it through peer review, you have some reason to trust it. In the leak and social media ecosystem, there's no bottleneck. Someone posts a claim. It's interesting, so people share it. Within hours, millions have seen it. There's no gatekeeping, no quality control, no verification. This can be good. It enables rapid communication and democratizes information. But it also means false or misleading claims spread just as easily as true ones. And once a false claim is out there, correcting it is nearly impossible. People remember the exciting story, not the boring retraction. Instrument trust is another crucial element. In particle physics, detectors are incredibly complex. They have millions of channels, intricate readout electronics, and processing pipelines that transform raw signals into physics measurements. Mistakes can happen at any stage. So the community has developed practices to ensure trust, detailed documentation of detector design, calibration procedures, and data processing, comparisons between different detectors measuring the same thing, regular cross-checks and audits. This infrastructure of verification means that when a particle physics experiment reports a result, you can dig into the methods and assess whether you believe them. Whisper should work the same way. The camera design is published, the calibration methods are documented, the data processing pipeline is described in technical papers. In principle, anyone with the raw data could reproduce the published images and verify that the processing was done correctly. But if the raw data for a specific event is unavailable, that chain of trust is broken. You can't verify. You have to take someone's word for it, and that's not how science works. Here's what the 3i Atlas case needs to look like if it's going to be taken seriously. First, raw Whisper data from the alleged missing window must be released publicly, not processed images, raw detector readouts. Let independent teams analyze them using their own methods. Second, all metadata and logs associated with that data must be provided. Timestamps, pointing information, exposure settings, quality flags, everything. Third, cross-checks with other instruments on Parker and elsewhere must be published. Did the magnetometer see anything unusual? Did plasma detectors pick up strange signatures? Did ground-based telescopes see anything during the same time period? Fourth, the mission team needs to issue a statement explaining what happened. If data was lost, how and why? If it was flagged as corrupted, what was the justification? If there was any manual intervention, who authorized it? And on what grounds? None of this has happened yet. Maybe it will. Maybe the institutional wheels are just turning slowly, and eventually there will be a proper scientific response. Or maybe the leak is baseless and there's nothing to respond to. Or maybe there's active suppression, and none of this will see the light of day without external pressure. We don't know, but we can compare to the neutrino case and see how different the standards are. In one case, rigorous, open, multiply verified science. In the other, rumors and missing data. If we care about truth, we need to insist on the higher standard. Not just for 3i Atlas, but for everything. Whether it's comets, particles, climate data, medical research, or any other domain where evidence matters, the principles are the same. Show your work, share your data, invite scrutiny, and don't expect to be believed until you've earned it through transparency and rigor. That's not being closed-minded. That's being scientific. Part 13. Parallel. Spacecraft Ops and Recent Launches. October 2025 was a busy month for space operations. Multiple missions were active. Parker continued its solar observations. The James Webb Space Telescope was conducting deep field surveys. Various Mars orbiters and rovers were working. Commercial satellite constellations were being deployed, and several new launches were scheduled. The space environment was also active. A significant solar flare erupted on October 9th, sending a coronal mass ejection toward Earth. Geomagnetic storms followed, affecting satellite communications and forcing some spacecraft to enter safe mode. This context matters because space operations are complicated and unpredictable. Things go wrong, not because of incompetence or malice, but because space is hard. Radiation damages electronics. Temperature swings stress materials. Communication is limited by distance and line of sight. Onboard storage is finite. Bandwidth is precious. Every mission operates under constraints, and teams constantly make tough decisions about priorities. When Parker is near the Sun, it faces extreme conditions. The heat shield protects critical components, but there are limits. If temperatures exceed design thresholds, instruments get powered down. If the spacecraft has to perform an emergency attitude adjustment, planned observations might be interrupted. If a solar event floods the environment with high-energy particles, detectors can saturate or get damaged. If telemetry buffers fill up because downlink windows are missed, data gets overwritten. These are routine operational challenges. Now, imagine you're on the Parker mission team in mid-October 2025. You're tracking the spacecraft's trajectory. You're aware that 3i Atlas will pass relatively close, which is scientifically interesting but not the primary mission objective. Whisper is scheduled to be operating during that time. Then the solar flare happens. You're monitoring the spacecraft's health. Radiation levels spike. Thermal sensors show elevated temperatures. One of the gyroscopes reports anomalous readings. You make a decision. Power down non-essential systems until the environment stabilizes. Whisper goes offline. 4 hours later, conditions improve and you power everything back up. But you've lost data during the window when 3i Atlas was closest. This scenario requires no conspiracy. It's just bad luck. The timing coincidence is unfortunate but explainable. Yet from outside, without access to internal mission logs, it looks suspicious. Why exactly during that window? The answer: random chance. Sometimes improbable things happen. Alternatively, consider data triage. Parker generates more data than it can transmit. The spacecraft has limited storage and limited communication bandwidth. Mission planners prioritize solar corona observations are highest priority because that's the mission's main science goal. Instrument health telemetry is critical. Everything else is secondary. If something has to be deprioritized to make room, it's the lower value data. Maybe WISPR was imaging the general background, including 3I Atlas, but the mission team didn't realize the significance until later. By then, the data had been overwritten by new observations. Again, no conspiracy required, just operational realities. Or consider a scenario where data was received but processing revealed issues. Cosmic ray hits corrupted several frames. Exposure settings were wrong, causing saturation. A software bug introduced artifacts. The quality control team flags the data as unreliable and marks it for exclusion from the public archive. This is standard practice. You don't release bad data that might mislead users. From the outside, this looks like suppression. From the inside, it's quality assurance. The distinction matters, but without transparency, you can't tell which is which. The point here is that there are many mundane explanations for missing data that don't involve deliberate censorship. Space missions are messy. They involve compromises, technical glitches, and imperfect decisions made under pressure with incomplete information. If we assume malice every time something goes wrong, we'll be wrong most of the time. But, and this is critical, assuming incompetence or bad luck is also not always correct. Sometimes there is intentional action. Sometimes data is suppressed for reasons that aren't technical. The challenge is distinguishing between these scenarios without access to internal information. Recent launch activity provides another angle. In late 2025, several space agencies and private companies were preparing missions that would involve close solar system exploration. ESA's Comet interceptor was in development. NASA was planning follow-up missions to the outer solar system. China was expanding its lunar and Mars programs. These missions take years to plan and execute. If 3I Atlas was confirmed to be artificial, there would be intense pressure to redirect resources toward intercepting it or similar objects. That could disrupt existing plans, create funding competitions, and force hard choices about priorities. From an institutional perspective, this creates a perverse incentive. If you're a mission team with limited resources, you might not want to highlight a discovery that would pull funding or attention away from your work. You might rationalize downplaying anomalies or waiting until you're more certain before announcing. This isn't a conspiracy to hide aliens, it's ordinary organizational behavior, protecting your project, your funding, your team. But the effect is the same. Information gets delayed or suppressed. This is why transparency mechanisms need to be structural, not dependent on individuals' good intentions. The system should make it difficult to hide data, even accidentally, even for benign reasons. Automatic archiving, third-party oversight, clear timelines for release, accountability when deadlines aren't met. If we leave it up to individuals to decide what to share and when, institutional pressures will sometimes lead to secrecy, even when that's not in the public interest. The recent solar flare example is also instructive. Space weather affects all missions. It's unpredictable and sometimes severe. If October 14th's data gap really was due to solar activity, that should be easy to verify. Space weather is monitored globally. Multiple satellites track solar flares, coronal mass ejections, and geomagnetic conditions. The data is public. Anyone can check whether there was unusual activity during the Parker 3I Atlas window. If there was, that supports the operational explanation. If there wasn't, that's suspicious. This kind of cross-check is exactly what should happen, but it requires someone with expertise and time to do the analysis. Part 14. Parallel, Policy and Funding. Let's talk about money, because money shapes everything. Parker Solar Probe's total mission cost is approximately $1.5 billion over its lifetime. That includes spacecraft development, launch, operations, and data analysis. It's funded primarily by NASA's Heliophysics division, which competes for budget allocations with other divisions: planetary science, astrophysics, earth science. Every year, these divisions justify their programs to Congress, NASA leadership, and ultimately the public. A successful mission generates scientific results. Papers published, discoveries announced, public engagement. These outputs justify continued funding. A mission that produces unexpected or controversial results faces a more complex situation. On one hand, discoveries attract attention, and can boost support. On the other hand, controversies can invite scrutiny, criticism, and political interference. Mission teams have to navigate this carefully. Now imagine you're a mission scientist. Your team has data suggesting something extraordinary, possible evidence of an artificial interstellar object. If you announce prematurely and you're wrong, your career suffers, your mission's credibility is damaged, and future funding might be jeopardized. If you announce and you're right, you've made the discovery of the century, but you've also created a media circus and probably lost control of the narrative. If you don't announce, hoping to gather more data first and the story leaks, you're accused of cover-up. There's no easy choice. Funding cycles exacerbate these pressures. NASA operates on annual budgets approved by Congress. Long-term planning is difficult when funding can change year to year based on political priorities. If a mission is seen as controversial or as distraction from core objectives, it might face budget cuts. This creates an incentive to stay focused on safe, predictable science and avoid rocking the boat. Recent policy developments affect this landscape. In 2025, there were discussions about increased transparency requirements for federally funded research. Proposed rules would mandate faster data release, public access to archives, and stronger accountability for data management. These proposals faced resistance from some institutions who argued they would be costly and burdensome. Others supported them as necessary for maintaining public trust. The outcome of these debates will shape how missions like Parker handle data in the future. International considerations matter too. Space science is increasingly collaborative. The Parker Solar Probe mission involves partners from Europe and other regions. If sensitive data needs to be released, decisions have to be coordinated across international boundaries. Different countries have different transparency norms and legal frameworks. What might be routine disclosure in one country could be restricted in another. This can create delays and complications. There's also the question of commercial interests. As private companies become more involved in space exploration, they bring proprietary concerns. If a mission uses commercial instruments or partners with private entities, data rights can be complicated. Who owns the data? Who decides what gets released? These issues are still being worked out, and they add layers of complexity to transparency. Funding also determines long-term data stewardship. Archiving data properly is expensive. It requires storage infrastructure, personnel to maintain it, software to access it, and regular updates as formats and technologies change. Once a mission ends, funding often dries up, and archives can degrade. Data gets lost not through malice, but through neglect. If we care about preserving data for future researchers, including data from events like the 3i Atlas flyby, we need sustained funding for archives even after missions conclude. Here's a concrete proposal. Every space mission should have a mandated data management plan that includes public release timelines, independent archive mirrors, and dedicated funding for long-term stewardship. The plan should be reviewed as part of mission approval and monitored throughout the mission's life. Non-compliance should have consequences: delayed funding, reduced allocations, or public reporting requirements. This makes transparency structural rather than optional. Another proposal: citizen science and public engagement should be integrated into missions from the start. If the public is invested in a mission, if people are actively analysing data and contributing to discoveries, there's built-in pressure for transparency. It becomes harder to hide data when thousands of amateur astronomers are watching and waiting. Missions like Galaxy Zoo and Planet Hunters have shown how effective public participation can be. The same approach could work for spacecraft data. Policy also needs to address whistleblowing. People who expose suppressed data or institutional misconduct should have protections, not punishments. Scientific institutions should have clear channels for raising concerns: independent ombudsman, review boards, external reporting mechanisms. If someone believes data is being improperly withheld, they should be able to escalate without fear of retaliation. This encourages accountability and makes cover-ups harder. Finally, there's the role of international agreements. Just as we have treaties governing nuclear weapons, outer space activities, and Antarctic research, we could have agreements on scientific data transparency. Signatories would commit to open data policies, mutual archive access, and collaborative analysis of major discoveries. This would create peer pressure. Countries or institutions that hide data would face criticism and isolation. It's not a perfect mechanism, but it's better than nothing. The 3i Atlas case, whether the suppression allegations are true or not, highlights gaps in our current system. We don't have strong enough transparency requirements, we don't have adequate protections for whistleblowers, we don't have robust independent oversight, and we don't have sufficient public engagement to create accountability. These are solvable problems if there's will to address them. The question is whether the institutions involved will act proactively, or whether it will take a crisis to force change. Part 15. Final synthesis, call to action, and one last tech news punch. We've travelled a long road together. We started with a missing 4-hour window, a clock ticking from 800 to 1200 Universal Time on October 14, 2025. We've examined the forensics of the data gap, the claims about what was allegedly seen, the natural explanations that might account for unusual features, and the extraordinary possibility that Parker photographed something artificial. We've explored institutional behaviour, whistleblowing, and transparency. We've drawn parallels to AGI development, particle physics, and operational realities of spacecraft. And now, we need to bring it all together and figure out what this means and what comes next. Let's be clear about what we know for certain. 3i Atlas is real. It's an interstellar visitor, the third confirmed object from beyond our solar system. Its orbit is hyperbolic, meaning it came from interstellar space and will return there. Ground-based telescopes have observed it extensively. Measurements show unusual composition, high carbon dioxide, strange polarization, behavior that doesn't quite match typical comets. These observations are peer-reviewed and published. They're not in dispute. Parker Solar Probe exists and was operational in October 2025. It was in a position where geometry would have allowed WISPR to image 3i Atlas during a close approach. This is also not in dispute. What remains unverified is everything about the alleged data gap and what the missing frames supposedly show. We have a leaked report claiming 4 hours of data were flagged as corrupted and removed from public archives. We have descriptions of thermal vents, hard shadows, and geometric structure. We have social media speculation and conspiracy theories. But we do not have the actual frames. We do not have official confirmation from the mission team. We do not have independent verification. So here's what this situation represents. A test case for how we handle extraordinary claims in an age of information abundance and institutional opacity. If the leak is false, if the data never existed, or if the gap has a mundane explanation, then we need to learn how to prevent false claims from spreading so easily. We need better media literacy, better fact-checking, and better communication from scientific institutions when controversies arise. If the leak is true, if data really was suppressed, then we need transparency reforms to prevent this from happening again and accountability for those responsible. Either way, there are lessons here. Let's summarize what would constitute compelling evidence for different hypotheses. For the natural comet hypothesis, high-resolution imaging showing typical comet features like an irregular nucleus, diffuse coma, chaotic jets, spectroscopy confirming water, CO, CO2, and organic molecules consistent with known comets. No detection of unusual electromagnetic emissions or non-gravitational accelerations beyond what outgassing explains. Multiple independent observations all consistent with a natural object. This would close the case. For the machine hypothesis, imaging showing clear geometric structure, regular spacing of features, sharp edges, and symmetry inconsistent with natural processes. Spectroscopy revealing non-natural materials, unusual isotopic ratios, or emissions inconsistent with cometary activity. Detection of artificial signals, radio transmissions, coherent electromagnetic emissions or encoded information. Non-gravitational acceleration patterns consistent with propulsion rather than outgassing. Multiple instruments on multiple platforms all detecting anomalies. And crucially, release of raw data allowing independent verification. This would open the case wide. Right now we're in between. We have suggestive anomalies but not proof. We have claims but not data. We have speculation but not consensus. And that's where transparency becomes critical. If the WISPR frames exist and show nothing unusual, releasing them settles the question. If they show something ambiguous, releasing them allows scientists to debate interpretations. If they show something extraordinary, releasing them starts the process of verification. The only scenario where withholding makes sense is if there's a concrete, justifiable reason beyond simple caution. And even then, the reason should be publicly stated and the withholding should be temporary. Here's the call to action, and it applies to everyone. Demand better. If you're a scientist, advocate for transparency in your institution. Push for open data, public archives, and clear communication. If you're a journalist, investigate these stories rigorously. Don't amplify leaks without verification, but also don't ignore them. Ask hard questions. Request data through formal channels. Hold institutions accountable. If you're a citizen, engage critically. Don't believe everything you see online, but don't dismiss possibilities just because they're unusual. Support policies and politicians who prioritize scientific transparency. Use Freedom of Information Act requests or equivalent mechanisms in your country to demand access to public data. For those with technical skills, do your own analysis. The Whisper archive is public. Download the data, check for gaps, look at metadata, compare different time periods. If you find something suspicious, document it and share your findings. Peer review isn't just for professional scientists. The community of people who care about evidence can collectively verify or debunk claims. This is how open science is supposed to work. Now, one final punch, a contemporary hook, to tie this all together. In late November 2025, OpenAI announced new transparency initiatives for AI development. Public release of safety testing results, third-party audits of model behavior, and a commitment to disclosing known risks. This came after mounting pressure from researchers, regulators, and the public. The announcement was seen as a significant, if incomplete, step toward addressing concerns about opacity in AI development. Whether it's meaningful or just public relations remains to be seen, but the direction is clear. Transparency is becoming a competitive advantage, not just an ethical obligation. This is the model we need for space science and every other field where public trust and high-stakes decisions intersect. Openness as default, secrecy as exception, verification as standard practice. If institutions internalize these principles, we'll be better prepared for whatever comes next, whether it's comets, AI breakthroughs, or something we haven't imagined yet. So let's return to where we started, that 4-hour window on October 14th. The data might be corrupted, it might be lost, it might be hidden, or it might show something that changes everything. We don't know, but we should know. The tools exist, the resources exist. What's missing is will, and will comes from pressure, from people insisting that questions deserve answers, from communities refusing to accept opacity as acceptable. When the archive eventually opens, if it opens, we might see dust and ice, the mundane reality of a comet doing what comets do, or we might see something else. Flat panels catching sunlight, vents glowing against the corona, a dark hull silhouetted against solar fire, dumping heat, surviving the inferno, sailing through our system on a journey that began light years away. We might see a machine. We might see proof that we're not alone, that intelligence is out there, building things, travelling between stars, maybe watching us even now. But until those frames are released, until someone with access decides that transparency matters more than caution, or secrecy, or institutional inertia, all we have is this: questions, possibilities, and the uncomfortable knowledge that the most important images in human history might be sitting in a database somewhere, flagged as corrupted, waiting. The real power isn't in the answers, it's in refusing to stop asking. When the archive opens, if it opens, will we see dust or a dark ship? The uncertainty is unbearable, but it's also the point. Stay curious, demand data, and never, ever stop looking up.